silicon micromachining high Q factor millimeter wave uh, filters. First of all, I will talk about different ways of the fabricating over millimeter wave filters. Uh, I give you some examples of different methods of the fabrication. First of all, the CNC milling. As you can see in this example, is the paper in 2020, I think so. And this is a bucket structure, and you people get good result, kind of good result in 350 gigahertz. But the structure, as you can see, is comparable to the coin and it's bulky. The other way to fabricate is using different 3D printing methods, and in these ways, again, the structure would be bulky, but in the graph you will see the parameter, you will see that they get some filtering response at 180 gigahertz. Another ways is laser beam machining methods. That's here I bring another example of it, and as you can see, this method also gives you a good filtering response at millimeter wave frequencies and with bulky structure. There's other ways to also fabricate our millimeter wave filter in the planar way or much smaller way, but of course with the comparable result. As you can see here, this is our one filter in 270 gigahertz from our group, and another way to fabricate planar structure in this high frequency range is using U8 photoresist machining. Also, you will see a lot of papers about this and a lot of people working on it. And it's you can see there's a result of one example I'll bring to you. But today I will talk about silicon micromachining. Why we choose the silicon micromachining for our work is just because of it's a planar structure and very robust in the fabrication, and it allows us to have 3D geometries or 2.5 or 2.5 geometries, and also we can produce a lot of them together. It's massive production way, and we shows that we could achieve very low loss structure. So then I will go through the fabrication and how we do the silicon micromachining. First of all, we use the SOI wafer, silicon on isolator wafer, and a silicon isolator wafer consists of 2 layers of silicon and oxide sandwich between these two. First step is to oxidize these wafers. I will explain in the next slides why we do that. But from the picture, you can see that this is the silicon wafer. When we put the oxide, the color will be changed, of course. And after that, we will do the lithography to pattern the wafer. We use the photoresist, a positive or negative. It depends on the tools that we use and the method and the pattern. We put the photoresist and then etch the oxide that we put on the silicon wafer. Why? Because we need hard mask. We need hard mask to etch silicon because the silicon is thick enough in different wafers. You could order different thickness, but normally it's around 200, 100 micrometers, 2, 4, 5, 600 micrometers. It's different. And to etch this kind of that much thickness silicon, you need a hard mask. It couldn't be happening with the photoresist. So then the next step is deep reacting ion etching, DRIE. In this step, we etch the silicon to make our cavities. In this picture, as I'll show you, imagine that this is the top part of the cavity, resonator cavity. We just etch it, the silicon from the top and bottom. And the next step is to put gold on everywhere. Then we would have a structure with a metallized structure. The only thing we should do next is to put this layer together to get our filter, or get to make a resonator, a cavity. Here you can see that I do that by my hand in our lab, but normally in companies they use tools. They have a lot of tools to do that, and it's very easy. For us, I will do it by my hand, and now I'm pretty expert on it. So here you can see a picture of 6 layers of chips on top of each other. We use some alignment stuff to align, to control the alignment between these layers. And then after that, we have measurement. So the only thing that remains to measure this structure after the bonding. Actually, when we put these layers on top of each other, we put them in the oven to kind of melt the gold between them, and this layer will be attached to each other. Then we can measure it. Then we have our filter. So now I will go through some of the filters, some of the examples that I work on it. First of all, this is a filter that we designed and fabricated, as you can see through the picture. This filter is the functional bandwidth of this filter is 0.5. We choose this functional bandwidth to show that the tolerance of the fabrication, or the silicon machining fabrication, is quite low to could kind of achieve this functional bandwidth, low functional bandwidth. And we choose the 183 gigahertz. And through the simulation, we achieved 1,500 Q. It's still, I didn't measure this chip, but I will do that for the next because I think so. In this structure, I used the high order mode resonator with the, as you can see, the mode TE303. In this mode, you can achieve a better Q factor rather than the lower mode resonators. And but the problem of this using this high order mode is that you would see a lot of spurious or a lot of modes inside your band pass, and you don't want to, I mean, you want to avoid them. So we use a method to we use a method on the transition from the output and input to the first resonator, and then we adjust some of the coupling through the slots to remove almost all of the spurious in our band from 140 to 220 gigahertz, as you can see. So the next step, one of the important parts of the fabrication, that's one thing that we couldn't avoid, is underetching. And the underetching is one of our big problems, because it's not predictable, as you can, and it could be changed by pattern and recipe that we use for fabrication. In this picture that I got from the STM, you will see that we have same structure in top picture. We have same structure, same iris between two cavities. These two are cavity, and this is iris. And we etch this cavity, and we have this underedge. We call it underedge, and we don't have straight wire. So in the difference between these two pictures is that I use different recipe. For the same structure, you see that it could be, we could have 43 micron, 2 micron underage, or we could just have 10 micrometer underage. So, and this underage also will be changed by the pattern or by the size of the cavity and the thickness of the silicon and the place in the wafer, which part of the wafer, the different part of the wafer has different underage. So we have this is a big problem. Here also you can see the same different structure, but in these two structures we use same recipe, and the underage in the bottom one is around 20, but in the top picture in this structure in this iris we have 43. That's very difference between them. So we introduce a new method to kind of concentrate this the problem and solve this problem. This is a filter. We use big cavities, so the frequency will be lower, at 76 to 77 gigahertz, with the bandwidth of 1.3 person. In this structure, we could, as you can see from the fabrication, measurement and simulation, we could do something to avoid shifting in frequency and shifting in the coupling. With this structure is a kind of 3-layer chip. This 3-layer chip, where the first and top layer we had underage, and we used a middle layer as a followed structure to decrease the underage. And the Q factor, measured Q factor of this structure is 850. And yes, and you can see the result. The measurement and simulation are on top of each other, and I think this is good. Thank you for listening. Here for answering your question. Thank you, Arish.
Thank you for the interesting presentation, Mohammed. So the floor is now open for the questions. Is there any question? I don't see any questions. Is there? So, Mohammed, I just want to ask you a question. Did you at any step during your studies, did you make any test bench models to just figure out, how to resolve this underaging?
Yes, I can say that one of the way to avoid the underage is to repeat fabrication and measure. So we call it testing. Of course, we can do that. We could order a mask, do the fabrication, and measure the underage with a certain recipe. Then again, repeat it. I mean, repeat the mask and repeat all the things. But the problem is that it is not, I mean, not cheap. You have to repeat the fabrication, you have to repeat your mask, and it could be not one time, could be several times to achieve the good result. But with this method that we proposed, that you could, the first time, without any test, without anything, we reach the, I mean, our response is exactly the same. And normally with underage, the cavity will be bigger than, so you will have shifting in the S parameters. And yeah, in our previous test, you would see that we got shift